Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe electric field lines and why they're useful. So, pretty simple picture I've got here. Right now, just imagine a positively charged point charge in the middle of the screen. Now, for the sake of example, it doesn't matter if it's positively charged or negatively charged. All that reverses is the electric field directions. And before I move on here, I'm going to draw some electric field vectors. So if I pick a point like right here, boom. We know that, remember, the electric field is the field direction on a pretend positive point charge. So we pretend like we put a positive charge here and ask ourselves, what direction would the Coulomb force be? And the answer is to the right, because plus plus. Therefore, the electric field direction at this point is this way. I could draw that, label it with E for electric field. All right, now imagine I come down here, same distance. And now if I put a positive charge there, just by observation, I know that the force will be down, so the electric field direction is down. Right? And if I pick a point over here that's roughly the same distance, the electric field vector would be to the left. If I draw one right here, again, the same distance, to within reason, the electric field vector would point up. If I move over to here, again, trying to keep this distance the same, the electric field vector would look like this. And if I move over here, boom. If I move over here, the electric field vector would be basically this way, here, this way, and so forth. Now, this is just a hand sketch. It's not perfect, but the intention here is that if every one of these points around this circle is basically exactly the same distance away, the electric field vectors should all be the same length. Imagine now that I go further out and I do another circle. It's going to look pretty darn similar. However, a big difference, big difference is the electric field vectors would be smaller. If I go further out, the electric field vectors away but smaller. If I go further out, field is still away but smaller. The further out I get from this charge, the weaker the electric field. Right? So electric field lines are lines that we draw to help us visualize the electric fields. And if I were to draw the electric field lines for this point charge, they might look something like this. I'm going to draw them and then talk about the rules for drawing them. Right? They would look like so. I'm going to put this right at the center of this charge so that I can use my little tool here. Okay, let me get the field lines drawn and then I'll talk more about what they mean. Alright, I'm going to draw just this amount here. Right, so these lines that I have drawn, they're referred to as electric field lines. They're not themselves vectors, but they do have a direction. I'm going to go ahead and put arrows in here to indicate the directions. Right? And the field lines are just a way of visualizing the electric field. There's two important rules for field lines. Rule number one, the magnitude of the electric field is directly proportional to the number of field lines per unit volume. Now, it's it's kind of a tough thing to understand, I think, visualizing this in 3D, but what you have to imagine is this. Imagine like maybe a small sphere here, right? And in theory, there's a certain number of field lines going through that sphere. If I move the sphere closer, and notice how the field lines, as I get closer, the field lines are closer together. There would be more field lines going through that sphere, hence stronger field. So basically, when you're looking at field lines, you're looking for where the field lines are close together. The closer the field lines, the stronger the field. So in this region, the field is relatively strong because, graphically here, see how the spacing is relatively small compared to if I move out here and I look at the same spacing. Now I'm kind of describing this in 2D when you look at spacing. When you draw field lines, you're going to be looking at two-dimensional drawings. Technically it's per unit volume, but in fact when you draw the field lines, the spacing on the page, as the spacing goes down, that means stronger field. As the spacing goes up, it means weaker field. Another important thing about field lines is this. Electric field vectors are tangent to the curve. are tangent to the field lines. So what that means, if I look at this electric field line right here, if I pick a point like right here, the electric field vector would point this way. Whoops, that's not. Draw that as tangent as I can. Whoops, I did it again. I guess I got to move my arm more. Tangent to the field line. So the electric field vector would point like so. So these are the two most important thing about electric field lines. I think what I'll do here is stop this, look at a couple more cases. Give me a moment to change my picture. Hey folks, I'm back. So in this example here, I just want to talk about how to interpret field lines. So I've got an example, some field lines drawn. Now what I don't want to worry about is what would be causing these, how would we get a field like that. That's not the point of this discussion at all. All I want to talk about is how to interpret it. So given these being electric field lines, we're going to look at electric field vectors at A, B, and the point C. So I'm going to draw the electric field vectors in red, starting with A. If I were to draw an electric field vector at A, you'll notice the field line, the directions given. The electric field vector to A needs to be tangent to the field line. Might look something like that. It's supposed to be tangent right there. Tangent at that point. I gave it a certain length. Now, the length that I drew is somewhat arbitrary. Now I'm going to move over to point B here, which is this point is what I had meant that to be. And again, the electric field vector is tangent to the field line, so it's going to be something like this. Notice, however, if I draw like a little area here, like so, you notice 1, 2, about 3 field lines go through that area. And if I come over here and I draw kind of the same area, I've only got 1 field line going through it. So the field line at B is, really roughly, it's got to be about 3 times stronger. So when I draw this electric field vector tangent to the curve and quite a bit stronger field, so I'll just put quite a bit larger vector there. Right. We're going to move over to C now. You'll see that point C, tangent to the field line, is going to look something like this. And C, over at C, the field's very sparse. There's not many field lines here. If I draw the same area here, very, very, very weak field. The spacing is, probably half of the spacing that we have over here at A. So I'm going to draw a field vector that's tangent to the curve, and maybe real roughly half the length of electric field vector C. So important things, just understanding how to visualize electric fields based on the field lines. The field vector is always tangent to the curve. Could have did a better job here with this example, but I think this one shows it reasonably well. This one shows it reasonably well. And where the spacing is tight together, that means strong field. Spacing very sparse. These things really spread out, relatively weak field. Those are the important thing about electric field lines. I'm going to go ahead and pause this, take a look at one more example, and call this video done. Alright, I'm back, and I've got, not the best diagram I've ever drawn, but it's good enough for the discussion here. And what this is a picture of is just a quick sketch of what the field lines look like around an electric dipole. So simply put, an electric dipole really is just a positive charge, negative charge, same magnitude, separated by a small distance. The field lines around it, all I want to talk about right now are how to interpret the field lines. That's just the purpose of this. So I'm going to talk about electric dipoles in more detail later on. But for now, we're just going to talk about how to interpret the electric fields around this dipole. So in this region right here, you'll notice that the fields are very close together, the field lines. So the electric fields are very strong in this region. So if I were to pick a point like right here, the electric field is tangent to the curve, relatively strong field. If I pick another point, maybe out here somewhere, you notice that the field lines are separated by quite a bit more. That means that the field is weaker. The field's still tangent to the curve, so if I were to draw a field line at this point, or I'm sorry, not a field line, an electric field vector, it might look something like that. So there's an electric field vector, there's another electric field vector. If I were to draw an electric field vector out maybe here, again, this is a really sparse region here. The field lines are not tight at all. The field is tangent to the curve, but relatively weak. So again, that's how you interpret the field lines. Where they're close together, like in this region, the field relatively strong. Out in this region, like here, relatively weak. You'll notice there's hardly any field lines, or basically none on the endpoints. That's because, if I pick a spot like right here, field produced at that point by this charge is to the left, field produced by this charge to the right. The first field's definitely stronger, but the field is relatively weak in this region because the electric fields produced by these two charges are in opposite directions. In this region, the field is very, very strong because the electric field produced by the individual charges are both to the right, so they're more additive. And again, the purpose of this video is not to talk about the dipole. I'll make another video about electric dipoles, but the purpose of this video is, looking at some field lines, how do you interpret it? And I went through those examples. Hopefully this video helped clear that up. Everybody have a great day.